What are confidence intervals? Here's a simple explainer. Let's say we are interested in estimating some parameter theta about the population, but we have only some IID samples from the population, IID being independent and identically distributed. Since we are estimating theta using samples, there will be an inherent error in our estimate, and confidence intervals allow us to make a statement about this uncertainty. A confidence interval is a random interval, in this case mu of x, comma v of x, such that it contains the true theta with at least some probability gamma. Right? It's important to note here that the bounds of this interval, mu of x and v of x, are both random variables. A good way to think about this is to think of repeatedly constructing the confidence intervals. So in that case, so basically something like this, right? You keep constructing the confidence intervals. Now, the statement from the previous slide basically says that the true theta lies within at least a gamma fraction of these confidence intervals in the limit, right? At least a gamma fraction of these confidence intervals will contain the true theta in the limit. Okay, so now that we know what confidence intervals are, how do we construct it from the actual samples? So let's consider a simple case. Suppose the population distribution is normal with a mean mu and variance sigma square, and the sigma square is known to us, right? And we want to estimate this mu from a set of samples drawn from this distribution x1 to xn, right? So since mu is the mean, a natural estimator for mu from these samples is to just take the sample average. But how confident can we be about the estimated x bar? This is where confidence intervals are helpful. We can treat each xi as a sample from n of mu sigma square due to the IID assumption. Then due to the property of normal distributions, we have that the sum of n IID normal random variables is also normal with mean n mu and variance n sigma square. But since the sum of these n random variables, n normal random variables is nx bar, we have that nx bar is distributed as per this, and we can divide on both sides by n, and we get this. So since x bar is normally distributed with mean mu and variance sigma square by n, due to the property of normal random variables, we have that x bar minus mu by sigma by root n is has a standard normal distribution. So now that we know this, we can now ask the question of how do we construct an interval with say 95% confidence, right? So here is a standard normal distribution, and we want to choose in this case, let's say a two-sided interval such that the probability that z, which is the standard normal variable that we have created here, is between some z alpha minus z alpha and plus z alpha is at least 95%. So it turns out that for the standard normal distribution, this z alpha is 1.96, right? So the probability that z is between minus 1.96 and plus 1.96 is 95%. Now, therefore, our z alpha is 1.96. So now we can substitute back the definition of z into this expression from the previous slide, and we'll have a probabilistic statement about mu once we rearrange a little bit. So this basically says that the probability that the true mu is between x bar minus this quantity and x bar plus this quantity is 1 minus alpha, or 95%. And that's it. We have constructed our confidence interval. The confidence interval is x bar minus this quantity and x bar plus this quantity, and it contains the true mu with at least a 95% probability. And this quantity, sigma by root n, is sometimes called or often called the standard error.